Hello everyone, welcome back to my channel Risk Modeling Hub. If you are new here, I create content to help both beginners and professionals prepare for credit risk interviews and build strong fundamentals in risk modeling. So make sure to subscribe to my channel and hit the bell icon so you never miss an update. Today we will be discussing how to master binning and determine the predictive signals from it. This is very important concept in credit risk. So let me start with a quick thought experiment. Imagine two borrowers. One has a debt to income ratio of 12% and another has 13%. Do you think the risk difference between them is significant? Probably not. But now compare 12% with 55%. That's a completely different story. This is exactly why raw numbers can be misleading in credit scoring. Raw features like age, income, or debt ratios often don't behave nicely. They can be non-linear, full of outliers, and hard to interpret directly. Banks don't want unstable models, so instead of using raw values, they transform them into meaningful categories or risk tiers. That's where the binning comes into the picture. So, in this session, I will walk you through four key techniques: fixed width binning using pd.cut, quantile based binning with pd.qcut, grouping categorical variables, and finally, supervised versus unsupervised binning approaches. And by the end, you will see how these methods turn messy data into clear signals that models can you actually use. So think of binning as organizing a messy wardrobe. Instead of having clothes scattered everywhere, you group them into categories: shirts, trousers, jackets. Suddenly, it's easier to find out what you need. So, in credit risk, binning does the same thing. It brings stability, makes monitoring easier, handles outlier explicitly, and even simplifies deployment through lookup tables. Here's a quick question for you. If you were building a scorecard, would you rather deal with thousands of unique income values or just a handful of income brackets? Exactly. Brackets are easier to interpret, and that's the power of binning. Now that we understand why binning is essential, let's move into its deep understanding. I'll show how a simple function like pd.cut can transform the continuous variables like age into risk tiers that make sense for credit scoring. So now that we have seen why raw numbers can be misleading, let's answer the next big question. What exactly is binning? So think of it as turning a messy stream of numbers into neat little buckets that actually make sense. Formally, binning is the process of grouping continuous or categorical values into discrete buckets or bins. So instead of treating every single raw number as unique, we cluster them into ranges or categories. This makes the data more manageable and interpretable. And in credit scoring, it helps us see risk signals more clearly. Take age for instance. If you look at the ages 25, 26, and 27 separately, they don't tell us much. But if we group them into bracket like 25 to 34 bucket, suddenly we have a meaningful category that can be analyzed as a risk tier. That's binning in action. So there are different ways to create these bins. Equal width, where bins are fixed in size, like slicing a cake into equal pieces. Quantiles, where each bin has the same number of observations, like dividing a classroom into equal groups. Domain driven, where business rules guide the bins. For example, banks might define income brackets based on lending policies. And model driven, where bins are chosen based on how well they separate risk outcomes. So why go through all this effort? Because binning smoothens out the patterns, reduces the number of parameters, and makes the model easier to interpret. It also helps handle outliers and missing values, which are common headaches in real world data. And perhaps most importantly, it makes deployment and monitoring simpler. Stakeholders can actually understand what the binning means. So let me ask you, if you were explaining a credit scorecard to a non-technical manager, would they prefer to see thousands of raw income values or just a few clear income brackets? Exactly. Bins make the story easier to tell and easier to trust. So binning is not just a technical trick, it's a bridge between the raw data and meaningful risk signals. Next, we will deep dive into why binning matters in credit risk. Alright, we have defined what binning is and explored different strategies. But let's pause for a moment and ask, why does binning really matter in credit risk? Why do banks and regulators care so much about this step? So there are five big reasons. Stability and robustness. Raw variables can be noisy, but bins smooth things out and improve the monotonicity of default probabilities. Outlier handling. Extreme values don't distort the model, they are placed in their own bins. Interpretability. Regulators and business partners love clear categories. It's much easier to explain a high risk bin than a raw number like 47.3%. Scorecard methods. Binning enables techniques like weight of evidence and information value, which are the backbone of scorecard modeling. Deployment simplification. Bins can be stored in lookup tables, making models more robust against the data drift. So think of debt to income ratio. A raw DTI of 45% doesn't mean much on its own, but once you bin it into a high risk category, it immediately signals danger. And when you look across the bins, you will notice something powerful. Default rates increase consistently as you move from low risk to high risk bins. That's called PD monotonicity. And it's a sign of stable, trustworthy model. Also, it shows model stability, that is, by giving consistent performance over time. So, here's a quick check in. If you were monitoring a scorecard over time, would you rather track thousands of raw values or just a handful of bins that clearly show risk trends? Exactly. Bins make monitoring not only easier but also more reliable. So, binning isn't just a pre processing trick, it's the foundation of stable, interpretable, and regulator friendly credit risk models. Next, we will see how Python implements these ideas step by step, starting with pd.cut and pd.qcut. So, we just discussed why binning is so important in credit risk. Now, let's roll up our sleeves and see how it's actually done in Python. One of the most common tools we used is pd.cut, and it's preferred for continuous variables like age. Here's how it works. With pd.cut, you explicitly define the boundaries of your bins. For example, you might split ages into brackets like 18 to 24, 25 to 34, 35 to 49, and 50 plus. This is especially useful when business rules or regulators dictate specific cutoffs. Think of it like drawing lines on a ruler. You decide exactly where the divisions go. And in the code here, we have defined bins and labels and then applied pd.cut to the age column. Notice the parameters. Right is equal to false makes the intervals left close. So 25 falls into the 25 to 34 bin. Include lowest equal to true. This ensures the very first value, like 18, is included properly. This level of control is what makes pd.cut so powerful for business driven thresholds. But here's a common pitfall. If your data is skewed, some bins might end up empty. Imagine defining a bracket for ages 90 to 100 when your dataset has no one that old. That bin will be useless. So, always check your value counts to make sure that the bins are populated. Let me ask you, if you were designing bins for income, would you prefer equal with brackets like 0 to 50k, 50 to 100k, or would you rather define based on business rules like low income, middle income, and high income? That choice depends on whether you want mathematical precision or business interpretability. So pd.cut gives us fixed width and business defined thresholds with precise control. Next, we will look at pd.qcut, which takes a different approach, dividing the data into quantiles so each bin has the same number of observations. We just saw how pd.cut helps us create bins based on fixed thresholds. But what if our data is skewed or we want each bin to contain roughly the same number of observations? That's where pd.qcut comes into the picture. Unlike pd.cut, which slices data by fixed edges, pd.qcut uses quantiles. That means each bin has approximately the same number of records. For example, if we split income into 5 bins, each bin will hold about 20% of the data. This makes it robust against the skewed distributions and avoids the problem of empty bins. In the code here, we are creating 5 quantile based bins for income. Notice the parameters. Q equal to 5 means quintiles. 5 equal frequency bins. Red bins equal to true returns the bin edges, so we can reuse them later. And duplicates is equal to drop is a safeguard in case quantiles overlap, preventing the errors. Then when we apply the same bins to the test set, we use those same edges to avoid leakage. That ensures the consistency between training and testing data. Think of it like dividing a classroom into 5 groups, each with the same number of students. So even if some students are much taller or shorter than the others, each group still has equal size. That's the power of quantile binning. It balances the distribution. So a quick thought. If you had income data ranging from $5,000 to let's say $500,000, would fixed width bins capture the risk patterns well? I think probably not. The lower bins would be overcrowded and the higher ones nearly empty. But with quantile binning, each bin represents an equal slice of the population, making comparisons fairer. So, pd.qcut is your go-to. So, pd.qcut is your go-to when data is skewed or unevenly distributed. Next, we will explore when to use pd.cut and when to use pd.qcut, because a clear difference in our mind is necessary for better application into the models. So we have now seen how pd.cut works with fixed thresholds and how pd.qcut balances the skewed data with quantiles. But the real question is, when should you use what? So let's break it down. Start with pd.cut. This is your go-to when business rules or regulatory cutoffs matter. For example, in mortgages, loan to value ratios of 80% or 90% are critical thresholds. pd.cut lets you define those exact edges. It's intuitive, business friendly, and keeps natural meaning. The downside is If your data is skewed, you might end up with sparse or even empty bins, and it's sensitive to outliers. On the other hand, pd.qcut shines when your data is unevenly distributed. It ensures each bin has roughly the same number of observations, making it robust to skews and the outliers. That means no empty bins. The trade-off is that the bin edges vary depending on your dataset, which can make them less interpretable for business stakeholders. Think of it like slicing a cake. pd.cut is like cutting the cake into fixed size slices. Maybe some slices are huge, some tiny, depending on how the cake is shaped. pd.qcut is like making sure each person gets the same amount of cake, even if the slices look different. So one is business driven, while the other is distribution driven. So here's a quick thought. If you were explaining risk bins to a regulator, would you prefer fixed thresholds like LTV above 90% is high risk, or quantile based bins that change depending on the dataset? Regulators usually prefer fixed thresholds, but analysts love quantiles for balanced modeling. The choice depends on your audience and your goal. So the takeaway is simple. Use pd.cut when business defined thresholds matter, and pd.qcut when you want balanced bins for skewed data. Next, we will move on to understanding the business intuitions, which will help us in understanding how we are turning customers into risk tiers. So far, we have compared pd.cut and pd.qcut for continuous variables. But in practice, binning isn't just about functions. It's about building a structured workflow that transforms raw customer data into meaningful risk tiers. Let's walk through that process step by step. Stage 1 is explore. We begin with exploration. Imagine asking, does higher credit utilization imply higher probability of default? To answer, we look at the distribution of values and check the bad rate across them. This gives us the raw signal we need before creating bins. Next stage is course class. Here, we propose initial risk tiers, clear, stable, and explainable categories. For example, utilization below 10% might be low risk, while above 60% could be high risk. At this stage, we are defining boundaries that make sense both statistically and for business. Stage 3 is validate. So, the key check here is monotonicity. Does the probability of default increase consistently as we move across bins? If not, we refine until the trend is stable. This step ensures our bins are predictive and trustworthy. Next is documentation. So once validated, we log the thresholds. Documentation is critical as we persist the edges, explain the rationale, and prepare a monitoring plan. This makes the process transparent for regulators and ensure consistency in production. Finally, we deploy. The model goes live with binning logic embedded, and we monitor performance over time. This closes the loop from raw data to production ready risk signals. Think of it like traffic lights: green for safe utilization, yellow for moderate, orange for risky, and red for very high risk. Just as drivers instantly understand what each color means, stakeholders can quickly interpret these risk tiers. So, binning isn't just a coding exercise, it's a disciplined workflow that ensures stability, interpretability, and regulatory compliance. Next, we will look at how categorical variables are grouped, because not all features are continuous. So far, we have focused on continuous variables like age, income, or utilization. But not all features are numbers. Many are categoricals, like merchant codes, states, or product types. And here's the challenge: what do you do when you have hundreds or even thousands of categories? And that is why grouping matters. If we leave categories as they are, model becomes unstable, overfit to rare categories, and are impossible to interpret. Grouping solves this by reducing the dimensionality, improving stability, and making the results explainable to business stakeholders. So, first strategy is frequency based grouping, and this is the simplest approach. Rare categories, say merchant codes, that appear less than 1% of the time are collapsed into other bucket. So, this prevents the model from chasing the noise. And in Python, you can do this with a quick value count check and a threshold check. Another approach is business logic grouping. Here we use domain knowledge to map categories into meaningful clusters. For example, states can be grouped into regions or merchant codes into retail clusters. This makes the bins interpretable and align with how the business thinks. Finally, supervised merging. This is more advanced. We collapse categories that have similar bad rates, often using statistical tests like chi-square. The goal is to maximize the predictive power while keeping the categories manageable. So let me ask you, if you have 1000 merchant codes, would you rather explain each one separately to a regulator or group them into 5-10 clear clusters? Exactly. Grouping makes the story simpler and regulators prefer clarity over the complexity. So, categorical grouping is about striking a balance, reducing noise while keeping interpretability. Next, we will look at supervised versus unsupervised winning approaches, which combine both statistical rigor and business intuition. So, we have just explored how to group categorical variables. Now, let's take a further step and ask, should winning be guided purely by data distribution, or should it be optimized using the target variable? This brings us to supervised versus unsupervised winning. Unsupervised winning is target agnostic. It doesn't look at whether a customer defaulted or not. It simply splits the data using statistical methods like equal with bins, quantiles, or clustering. The big advantage is that it's safe, no risk of target leakage, no overfitting, and it's fast to implement. But the trade off is that it may miss important risk patterns because it's not tuned to the outcome we care about. Supervised winning, on the other hand, uses the target variable like default versus non default to optimize the win boundaries. This makes it much more predictive, helps enforce monotonicity, and strengthen the risk signal. The downside is that it can overfit if not validated carefully. So we need to use techniques like cross-validation or decision trees with constraints. So for example, you can use a decision tree classifier to extract optimal splits. By fitting the tree on a feature against the target, you get win boundaries that maximize the separation between good and bad customers. This is supervised winning in action. Think of it like teaching versus guessing. Unsupervised winning is like grouping students by height without knowing their grades. It's simple, but may not tell you much about the performance. Supervised winning is like grouping them by exam scores, directly tied to the outcome that you care about. So let me ask you, if you were building a scorecard for regulators, would you prefer the simplicity and safety of unsupervised bins or the stronger predictive power of supervised bins? The answer often depends on whether your priority is compliance or performance. So, supervised and unsupervised binning each have their place. The key is to balance the interpretability, predictive strength, and regulatory requirements. Next, we will look at Python workflow to understand end-to-end binning pipeline for better implementation. So, we have compared supervised and unsupervised binning strategies, but theory alone isn't enough. We need a practical production-ready workflow. Let's see how Python helps us build an end-to-end binning pipeline. The first step is splitting the data into train and test sets. Notice we stratify by the target variable to keep the default rate distribution consistent across both the sets. This ensures fair evaluation later. Next, we fit bins using the training data only. For example, pd.qcut with red bins equal to true gives us quantile based edges. This avoids leakage. We don't want the test set influencing the bin boundaries. Then we apply some edges to the test set using pd.cut. This guarantees the consistency between the train and test. So the model sees the same bin definition across the dataset. Real world data always has the missing values. So instead of ignoring them, we explicitly create a missing value category. This way, missingness itself can become a risk signal. We don't lose the information. Finally, we persist the edges. Finally, we persist the bin edges, labels, and versioning for deployment. Thinking of it as saving a recipe once defined. The bins can be reused consistently in production, ensuring stability over time. So imagine you are deploying a scorecard across multiple branches of a bank. Would you want each branch to define the bins differently or all of them to use same saved edges? Exactly. Consistency in key is the key, and that's why the persistent matters. So this pipeline takes us from raw data to production ready bins in a disciplined way. Next, we will connect this workflow to evaluate the bin quality, which will do all the necessary statistical checks and validation for optimal binning. So, we have built a pipeline to create the bins, but how do we know if those bins are actually good? This is where the evaluation comes into the picture, because not all bins are created equal. There are few critical checks we always perform. Count check. Each bin should have enough observation, at least 5% of the data or more than 200 records. Otherwise, the bin is too small to be reliable. Monotonicity. The bad rate should increase consistently across bins. If it doesn't, the bins may not reflect the risk properly. Predictive power metrics. We look at information value, KS statistic, and Gini coefficient to measure how strong the bins are. Visuals. Charts like WOE trends or bad rate plots help us see patterns clearly. So, information value or IV tells us how predictive a variable is. A value between zero point 0.2 and 0.1, 0.02 and 0.1 is weak, 0.1 to 0.3 is medium, and above 0.3 is strong. KS statistic measures how well we separate good and bad customers, while Gini coefficient shows the overall discrimination power of the model. Together, these metrics gives us full picture of bin quality. In Python, we can quickly validate the bins by calculating the bad rates and counts per bin, then checking the monotonicities. This ensures our bins aren't just mathematically neat, but statistically sound. So one should always check WOA trend line, which we will discuss, bad rate, bar chart, or distribution histogram and monotonicity check. So here's a quick thought. If you had a bin with only 50 customers, would you trust its bad rate to guide the lending decisions? Would you do that? Probably not. Small bins can be misleading, and that's why these checks are so important. So, evaluating the bin quality is about combining the statistical rigor with visual intuition. Next, we'll understand what are the common mistakes that can happen while performing the binning and how model risk is associated in binning. So, we just talked about how to evaluate the bin quality, but even with good check, there are common mistakes that can sneak in and compromise the entire model. Let's look at the biggest pitfalls and how to avoid them. Mistake first, overfitting with too many bins. So if we create too many bins, we end up with sparse data and noise capture. The fix is simple. Enforce a minimum sample size per bin, like 5% of the data, and check the monotonicity. Mistake number 2, data leakage from supervised bin. Another big risk is leakage. So if we tune bins using the full dataset, we are essentially peaking at the test set that inflates the performance artificially. So the solution is to fit bins on training data only and then apply them to test and validation sets. Mistake number 3, ignoring the missing values. Dropping or blindly imputing missing values is dangerous. Missingness itself can be a serious signal. The fix is to create a dedicated missing bin and analyze its bad rate separately. Mistake number 4, unstable bin edges. Bin the boundaries can drift the data over time. For example, income brackets that worked last year may not hold today. And to catch this, we monitor the PSI, the Population Stability Index. We'll discuss that and refresh the policies when needed. Mistake number 5, mixing the train or test edges. So finally, never mix train and test edges. If you use test data to define the bins, you have leaked the information. So always persist train edges and apply them consistently to test data. Think of it like building a noise. Think of it like building a house. Sorry, not noise. If the foundation shifts, the whole structure is at risk. Binning mistakes are those cracks in the foundation which are small at first but dangerous if ignored. So avoiding these pitfalls is just as important as building bins correctly. From the model risk checklist perspective, always validate bin stability and monotonicity before deployment. Next, we will go through some of the most important interview insights related to this topic so that anybody can ace the credit risk interview confidently. In the last we have seen the pitfalls to avoid the binning. Now let's shift our gears. But if you are in an interview and asked about these techniques, this slide summarizes the kinds of questions you will face and how to answer them with confidence. So first is, what's the difference between pd.cut and pd.qcut? Interviewers love this one. The key difference is that pd.cut creates fixed with bins, perfect for business thresholds like loan to value cutoffs. And pd.qcut, on the other hand, creates equal frequency bins, which are great for skewed data. The trick is to explain not just the mechanics, but when each is best used. Next is, how do you handle extreme skew and outliers in binning? So if asked about skew data, emphasize strategies like capping extreme values, using pd.qcut with safeguards like duplicates equal to drop, or creating the separate bins for the outliers. And always mention visualization, that is showing distributions before binning is a best practice. Next question is, how should you handle missing values in binning? This is a common trap question. The right answer is never drop missing values blindly. Instead, create a dedicated missing bin and analyze its bad rate separately. Bonus points if you mention patterns like MCAR, MAR, or MNAR. Next question is, how do you choose the number of bins? Here, balance is the key. Statistically, you want monotonicity and predictive strength. For that, IV and KS can guide you. But from a business perspective, each bin should have at least 5% of the data, and regulatory requirements often suggest 5 to 10 bins. Next is when to use supervised versus unsupervised binning. Frame this as a decision framework. Unsupervised is quick, safe, and avoids the leakage. Supervised is more predictive, but needs validation, like cross-validation to prevent overfitting. Show that you understand both the sides. Next is, what are the common binning mistakes to avoid? So finally, interviewers may ask about the pitfalls. Here you should mention overfitting with too many bins, leakage from using full data, and instability if you don't monitor the PSI. The solution is always validation with a holdout set. So imagine you are in an interview and asked, how would you handle missing values in binning? If you confidently say, I would create a dedicated missing bin and analyze its bad rate separately, you have shown here both technical knowledge and practical awareness. So, mastering these questions not only prepare you for the interviews but also reinforces best practices in real world modeling. So, alright, we have walked through binning, pitfalls, and even interview insights. But this isn't the end of the journey. It's just the beginning. Because once you have binned your variable, the next step is to transform them into the predictive variables using the weight of evidence and information value, WOE and IP. In the upcoming video, we'll deep dive into WOE and IV and how they convert bins into risk signals, enforce monotonicity, and quantify the predictive strength. And this is where scorecard really comes alive. So stay tuned because that's going to be a game changer. And here's a challenge for you in the meantime. Try creating 5 bins for credit utilization where the bad rate increases monotonically. Make sure your IV is greater than 0.1. I know that we haven't discussed IV in detail today, but do try at your end first. This exercise will help you connect today's binning concepts with tomorrow's WOE IV deep dive. By the way, if you'd like me to show a full Python demonstration of binning pipeline that we discussed today step by step, let me know in the comments. I would be happy to cover that part in detail. And before we wrap up, don't forget to subscribe to my channel and like this video. Share it with your friends who are preparing for credit risk interviews. The more we share the knowledge, the stronger we all become. So that's all for today. Practice the challenge. Stay tuned for WOE and IV deep dive. And as always, like, share and subscribe. See you in the next one. Thank you.